Hi, thanks for tuning in. The presentation is about a Glycol Dehydration P&ID. This is useful for a process engineer and operator of gas plant, designer and drafter. Today we'll talk about the controls shown on the P&ID, the safety features and the factors that will enhance the performance of gas dehy process. This is a typical Dehy P&ID for gas plants in Alberta, Canada. Elsewhere in the world, I wouldn't assume it will be very different. But if you are listening from outside Canada, you will have to follow the company's specifications for designing a similar P&ID. If you are new here, please consider subscribing. I request you kindly mention in the comments that you have subscribed. The purpose is to use the comment section of this video for further discussions and refinement of the process. So we are not going to discuss how the dehydration process is taking place. We are only going to discuss what is the purpose of some of the important controls used on the P&ID. So let's begin. This is the glycol contactor, and it is a 42-inch diameter and 30 feet high. It has 10 bubble cap trays and other standard internals as a standard Dehy glycol contactor. This is a boiler, 0.4 million BTU per hour or 400,000 BTU per hour. The design of a reboiler is so standardized in Canada that if you just tell the fabricator that you need a 400,000 BTU per hour reboiler, he will be able to build the remaining as required for dehydration. And these are inline centrifugal pumps. Their purpose is to boost the lean glycol pressure to the inlet pressure of the contactor and circulate a volume predetermined in the design stage. Other units shown are the gas glycol exchanger, filters, the sock filter and the carbon filter, rich lean glycol exchanger, glycol reservoir, flash tank, air exchanger, and a little vessel here to maintain the glycol level in this section of the contactor. Now we'll go to the instrumentation and control on each of the units. Let's start with the contactor. Inlet gas is usually from a compressor or from the gas well depending on the pressure. There should be a separator upstream of this glycol to remove the bulk of the water and other liquids, because this contactor will not be able to handle a lot of inlet liquids in this section. Since the gas is saturated at the temperature and water upon impinge on the inlet deflector here, the equilibrium will break out. The mechanical collision will break the equilibrium and liquids will break out of the gas phase. This piece of equipment right here will lighten the load of drying on the part of lean glycol. Throughout the design of this package, you will notice how units are placed in series to lighten the load of downstream equipment so that dew point is achieved. As soon as the gas enters the contactor, temperature and pressure will be displayed on the control room. This piece is relaying pressure to the control room. The following instruments are for this section of the contactor: a level transmitter, local level gauge, a snap-acting dump valve which removes all the breakout water described earlier. If there is an efficient removal of liquid upstream of the Dehy, then these instruments will have nothing to display. All these instruments are fitted so that there is a reading in the control room. Everything I just described is about removal of free water because We do not want free water to enter this section of the contactor. This section of the contactor is not designed for any particular amount of free water. So we are assuming that in case there is an upset of some kind upstream of the contactor, then there will be a carryover of some free water, and this section will remove that free water. Let's follow the gas path. The inlet gas that is at equilibrium, as described before, at the temperature and pressure, will pass through the coalescer just in case there should be any free water carry over with gas. The gas coming out from the coalescer is now more or less free of the free water. The arrangement given here is a chimney with an inverted cap. This is to prevent the gas shooting upward to the bubble cap trace and possibly damaging the plates. There is a level of glycol here, so gas enters that volume and rises up evenly. The velocity of the gas is reduced by this arrangement. Gas will evenly pass through the bubble cap trace against the downcoming lean glycol. During this process, water in the gas will get absorbed to the glycol phase. There are 10 bubble cap trays shown here. Lean glycol falls on the top tray and overflows a weir and falls into the second tray, and so on. By the time the glycol has reached the 10th tray, it's rich with water and needs to be taken out of the contactor for processing. The upward gas is losing water in stages, and by the time it comes to the first tray, the gas is at the desired water dew point. Dew point in Canada is usually 4 pounds per million standard cubic feet. This is not the same in all the gas plants. If the inlet gas is rich in hydrocarbons and the plant wants to make some money out of the condensate, then the dew point will be as low as 1 or less than 1 pound per million standard cubic feet of gas. This is due to the refrigeration section, where you don't want freezing of any liquid droplets in the refrige section. The gas now at the top of the contactor will be called the sales gas and is usually at a certain temperature based on the ambient. We don't mind heating the gas a little using the gas glycol exchanger here, which in turn helps. This exchanger is usually a pipe-in-pipe type with gas and glycol flowing counter current and exchange heat. The cooler the lean glycol gets, the better is the dehydration process. Therefore, the heat transfer area on the glycol side should be greater because you want the glycol to get colder. Sales gas is measured using the flow meter and recorded in standard conditions. The purpose of the back pressure control is to hold pressure upstream of the valve. There could be a pressure in the pipeline which can empty the pressure in the Dehy skid. Therefore, this valve maintains the pressure in the skid. Notice there is a blow-down valve here that will depressurize the contactor to 50% of its pressure, or 100 pounds in 15 minutes. This is a standard mentioned in API 521. If you want more details about that, you could go there. A process engineer is required to follow this code in designing all blow-down valves of pressure vessels. Some Dehy packages are fitted with a dew point analyzer at this point on the sales gas. It will not have any action but will maintain a dew point record of the sales gas. But most Dehy packages don't have that because an operator knows that if the temperatures are okay and circulation is okay, then gas is at the required dew point. Let's follow the glycol path first, and then we'll first do the rich glycol and then the lean glycol. Rich glycol has absorbed water that is lost from gas phase. That water needs to be removed so the same glycol can be reused in a continuous circulation. About 50% level is maintained here in this section so that gas does not flow in the wrong direction to the glycol side. This is achieved by all this mechanism shown here. The level control valve shown here has dual purpose. One, to maintain the level. Second, to drop the pressure of the glycol from the contactor pressure to the pressure required in the low pressure section, which is all of the units on this side of the P&ID. So all units here on the right side are low pressure units. You can see the spec brake right here. Perhaps this is the most important instrument here in the entire skid, the one that actually drops the pressure and also maintains the level. Since the lean glycol is hot and rich glycol is cold, in the next units the objective is to exchange heat one to another. If the rich glycol is heated a bit, it will reduce the burden on the reboiler. If the lean glycol is cooled, it will enhance the dehydration process. Therefore, it's a good idea to design the units in this way so that they are energy efficient. Notice the little coil here and the heat exchanger here. These two will reduce the lean glycol temperature and increase the rich glycol temperature. I'm aware for a new engineer the words are confusing: lean, rich, temperature, pressure. You'll have to go through the process a couple of times to get used to it. Following the rich glycol path from the coil, it will go to the filters. The sock filter will take out any solid particles. The carbon filter will absorb hydrocarbons, if any. Usually in a clean gas, there will not be any particles, and glycol is a poor absorber of hydrocarbons. So these filters are bypassed using this bypass arrangement. It's not bypassed all the time, but it's an operator's discretion when they want to change out the filter's elements, and then they can bypass it. One aspect to remember is to depressurize the filters before it can be opened for servicing or changing cartridge. There are many incidents reported for not following that procedure. Rich glycol from the filters will now pass through the packing in the reboiler section shown here. This packing is used to utilize the heat available in the steam rising up in the stack. All this is done to reduce the burden on the reboiler main duty. In the reboiler, the temperature is maintained at 400 degrees Fahrenheit or 205 degrees Celsius. Water boils at 100 degrees Celsius, so there is enough temperature for water to exit as steam through the reboiler column. This is how a rich glycol becomes lean glycol. While we are at the reboiler, all the arrangement you see here is standard in Canada. It goes by a code called CSA B149.3. This incorporates all the necessary safety to be included in the fuel gas train. Typically, all line heaters and reboilers will follow this code. The code essentially tells there should be a 2-level shutdown. one driven by gas and other manually. In addition to the fuel gas train being designed by code, there is a burner management control which has a complete management of maintaining temperatures and shutting down as required. This is again a standard for all reboilers. So let's continue the glycol path. Rich glycol is now the lean glycol exiting at nearly 200 degrees Celsius from the reboiler and needs to cool down to the contactor temperature. Typically the difference between the contactor temperature and lean glycol entering should be about 10 degrees Celsius. These are endpoints to set up in a HISS simulation if in case you're trying to do a simulation of the glycol dehy. Lean glycol flows out from this 3-inch nozzle to the stripping gas column. A small amount of fuel gas injected at the bottom of this column will absorb any moisture remaining in glycol phase. This is further explained in the GPSA if you are interested, where you can actually size the amount of gas that should go in as a stripping gas in order to enhance the dryness on the lean glycol. Because gas has an affinity for any water that this lean glycol is carrying out. In the exchanger, the surface area for cooling glycol is more than the surface area for heating. Cooling glycol is more important than heating glycol, since there is no other opportunity for glycol to cool down to contactor's temperature. Glycol reservoir is usually part of the package with reboiler. It has a fill connection which is used for startup of the unit. Lean glycol is cooled further in this fin pipe exchanger, also called the air exchanger. By the time glycol comes out to the pumps, it's around 80 to 100 degrees Celsius. It makes sense even in Canada to use the ambient temperature to cool the lean glycol because it's cold in Canada. In designing the pumps, the discharge pressure is an important factor. At the circulation rate determined in HISS simulation, the pumps should be able to deliver glycol with enough pressure to enter the contactor, which is at a high pressure. Temperature of lean glycol is further dropped in the gas glycol exchanger such that the temperature difference between the inlet gas and the lean glycol is maximum 10 degrees Celsius. If you can't meet this kind of endpoint temperatures in the lean glycol, then the dew point will be in question. The cooler the lean glycol gets, the better is the dew point of the sales gas. Lean glycol is then flowing down in the contactor tray by tray as described before. There are shutdown features available here only for liquid inlets. This is a dehydration unit and we don't want any liquids from the gas. Starting from the separator section in the contactor, this shutdown is for a high liquid level. As I mentioned before, the liquid only comes because there is an upset upstream of the glycol skid. Shut down at high liquid level in the flash tank again. There shouldn't be any liquids here. Probably this one is never activated in the entire life of the Dehy, but it's a safety requirement necessary there. So these are the controls and the important instrumentation here presented, and I have now come to the end of this presentation. I hope you have found some useful points to take away from this video. Again, I request you to comment and subscribe. See you in the next video.